a very good question at the end of the last lecture about this funny, delicate experiment where you flip the electron spins in a bar of iron. And if you do that, when the electron spins flip over, the bar of iron actually starts to rotate. And that's to emphasize that, you know, if you like, angular momentum of electron spins is perfectly real. The origin of it is a different story. And as I mentioned, we have to be a bit careful when we talk about the magnetic moments being due to circulations of charge. That doesn't really hang together with quantum mechanics. But where does that energy come from? Well, again, it's related. I hope you can remember all the way back to Faraday's law and this paradox where when we analysed this situation where somehow this current decayed and we got a dB by dt, a changing magnetic field, we got a circulating electric field, and that seemed to make the disk rotate. And that's in fact what happens in reality. The disk will rotate if we decrease the current in the coil, even though this mechanical system has not been touched at all. So the conservation of angular momentum here, basically the disk starts rotating precisely because the electromagnetic field has lost angular momentum and passed it into a mechanical system. And that's exactly what happens here, which is that if we flip the spins over, although we have to be very careful with the analogy that a magnetic moment is caused by a circulating charge, formally we can say it is. Of course, if we make the circulating the circulation of charge go in the opposite sense, which is effectively what we're doing when we flip the spins over, the mechanical system has to rotate in the opposite direction to maintain the total angular momentum of the universe. So that we've not gained some energy from somewhere out of the blue when we do this. And indeed, we can say that we've had to do work on the system precisely to flip the electron spins over. We've had to do work on the system with an external magnet to flip the spins over, and then when the spins flip over, the angular momentum gets passed to the mechanical system. I was also asked a more practical question. I've been pursuing this analogy between electric and magnetic dipoles. This was a view graph that I wrote quite recently. It's not on the VLE, but I'll either put it up or email it out to you because it is very useful to summarize the analogy between electric dipoles on one hand and magnetic dipoles on the other. Now, I'm going to concentrate for a couple of minutes on this idea of the energy in a B field. And basically, what happens is if you've got an unpaired electron spin or you've got an orbital angular momentum, a non-zero orbital angular momentum in the ground state of a material, the dipoles tend to line up with the magnetic field. Remember, there's some funny sign conventions associated with this. The lower energy state is when the dipole moment is parallel with the field. And in a sense, the paramagnets do behave like orientation polarization of dielectrics in water. You start off with a permanent magnetic moment and it tries to align itself with the field because that's a lower energy state, and indeed a torque is induced on it to pull it along the field direction. And so we would expect a relatively similar mathematics to apply to permanent dipoles as applies to permanent electric dipoles, which tend to get pulled in an electric field. And indeed, formally, there's a big similarity. This is what we would describe it as in a formal mathematical way, that the external field, because now the individual magnetic moments try to line up with the field, the external field produces a magnetization field within the material. Previously, dipoles have been aligned randomly in the material, and then when we put an external field across it, we produce a magnetization field inside the material. And that's very similar to if we put an external electric field on water, that the dipoles tend to line up, and that produces a polarization field in the water. So there are these similarities between the two systems. However, before I do the formal maths, in previous, you'll see if you look at the VLE notes, I did the formal maths of magnetism and then went over to say, well, there's some complications about it. This time, I'm going to go the other way round, and I'm going to start off with the complications and then talk about the formal approach in the second half of the lecture. Well, first of all, again, you won't be able to see the details of the periodic table from the back, but you can see it's a periodic table of the elements. It's deep in quantum mechanics why iron, cobalt, and nickel are the three ferromagnetic elements. We can't obviously hope to understand that from any classical point of view, and this is because of the way that the 3D electrons behave. Some of the electrons are released into a conduction band, as with normal metals, but this leaves the remaining, if you like, core electrons, but still they're banned to the nuclei, but they're still in a state which gives us a net spin angular momentum. And so in these materials, again, it's in you'll study this much more in the quantum mechanics next year. These particular materials, so iron, cobalt, and nickel, of course, iron is the most famous. That's why it's called ferromagnetism, from the Fe. I think the Latin name for iron was ferrum, and so ferromagnetism is usually thought of with iron, but cobalt and nickel, and indeed alloys of these three elements, are all ferromagnetic. And I want to distinguish from the outset that, of course, if you've got let's just say it's one electron spin. It's oversimplifying, but let's say there's a spin, and it will tend to line up parallel with the neighbouring spin. And you might think, well, this is just like the same phenomenon as if I've got a spin and I put an external B field on it. This is going to give us this kind of alignment. And there is an element of that involved, because this one makes a magnetic field that tends to align this one parallel to it. However, if it was purely classical, in the sense we can't even understand why the spin exists classically, but if this was just what was called an interaction energy between two magnetic dipoles, the ferromagnetism of, for example, nickel would disappear at about 0.25 Kelvin. So very close to absolute zero, there would be enough shaking of the lattice to completely break this parallel alignment. However, the actual ferromagnetic phase transition, where this loses its magnetism, is at over 600 Kelvin. It's a perfect stable ferromagnet at room temperature. And that is because the spins in these three materials are locked together by the Pauli exclusion principle. Again, something we cannot understand classically, and indeed can only understand with more advanced quantum mechanics, why it's just these three particular elements in the middle of the first transition series which have this particularly strong effect that locks the spins parallel. So yes, there's a weak direct effect that if this spin exists, this little magnet, it makes a magnetic field at the neighbouring magnet and tends to align it, but that's very, very weak. However, by the Pauli exclusion principle, the way this one is bonded to this one and this one's bonded to this one, and you get overlap between the atomic orbitals, locks these things in place by the Pauli principle. And so, although we do get a similar kind of mathematical effect, we can say, oh, well, this magnetization is produced by a B field. It's a very special quantum mechanical, and as I'll show in a minute, solid state physics type of effect. So what really happens in a bar of iron when you magnetize it is extremely complicated. And this is a typical magnetization and hysteresis curve for soft iron. So that equation applies to that bit there. There we go. That's the total range of validity. If you take this, I mean, ferromagnets are paramagnets in the sense that they behave paramagnetically. They enhance the magnetic field, but the enhancement effect is 1,000 to 1,000,000 times stronger than with any other material. And if you want to get a nice linear, I'll explain what the H field is in a minute, but roughly speaking, if you want a linear relationship between your applied field and the magnetization produced in the sample, you basically lose it very close to the origin. And you're starting here with an unmagnetized piece of iron. And we cannot hope to understand this curve without solid state physics as well as the electromagnetism we've studied so far. So what's going on in figure 133 is these are emphatically not individual electron spins. You're to imagine in this diagram that these grains, they're of the order of, let's say, a micron. So we know that atomic distances are in the 10 to the minus 9, between 10 to the minus 9 and 10 to the minus 10 of a meter. And within one domain, the spins are locked together like by the Pauli principle, as described here. And so you've got a block, and in a micron or so, we're talking about atomic dimensions of a few times 10 to the minus 10. These grains might be a few microns, a few times 10 to the minus 6. We're talking about 10 to the 4 in linear dimensions, and so in volume, one of these grains might be contain 10 to the 12 sort of atomic spins, and they are lined up. But when a real piece of iron is crystallized from the melt, you don't get one massive great single crystal. You get lots of microcrystals growing from different nucleation points, and then they reach a boundary where a different material, a different nucleation site, as for example, all the spins within here, these 10 to the 12 microspins are lined up, but in a different direction, and these are called domains, and you can see that the domains can have random orientations with respect to each other. And again, that's the analogy like with the water. The dipoles in water are molecular. They try to line up with the field. If we put an external field across this material, we can see that the domains start to align with each other. And this is what's called the magnetization curve. So the magnetization curve is when we start off with a bit of iron where we've got all the domains randomly oriented, and then as we put on, and you can see again, I'll come to this to say the formal part, the field strength is given in Gauss here. This is 1 here, and this is 10,000 here. So the magnetization that's produced is, if you like, the external field magnetization is very small indeed compared with the magnetization that you produce. You know, we could interpret this as the material having an enormous susceptibility. As you keep going up curve A here, this is called the magnetization curve, the domains are gradually aligning. And there's strong evidence for this being a domain type effect, because although it's always drawn as a smooth curve, you're going up through, and the magnetization curve looks like it's smooth. If you magnify any individual part of it, the magnetization actually goes up stepwise, and the stepwise magnetization is due to each little domain is actually reorienting as you apply the field. And you can imagine that's very complicated. There's strain energy associated with the boundary. You've got all these microcrystals growing together. And indeed, again, it's sort of taking these in slightly odd order. But if you magnetize, let's say we've got a piece of silicon steel, and that might have, silicon steel usually has a relative permeability of 5,000. In other words, the magnetization field is about 5,000 times the external field. If you start off with it unmagnetized and then you move a bar magnet next to it in order to align the fields, you can actually hear a series of clicks. The material, it's actually the strain energy in the lattice dissipates energy in the audio frequency range, and you actually hear a series of clicks if you connect this up to a loudspeaker. And these clicks are connected with these individual domains realigning in the external field. So there's a lot of phenomena in this curve. And that also, it's highly non-linear because eventually you reach saturation. Once you've got all of the domains aligned parallel, there's nowhere else to go. Once all the spins in the material are lined up parallel, then you cannot get any more magnetized than that. So you reach a saturation point and the curve basically flattens off. And now, you see again, what makes it problematic to apply all these formal equations is that the magnetization you get depends on the whole history of the piece of material. Because now, if having magnetized it, we proceed to demagnetize it, so now we've got, if you like, this state would be all the little domains have lined up parallel, and so this now produces a net massive magnetization because the whole material's lined up. We now apply a big B field in this or whatever size of B field we like in this direction in order to make the spins flip the other way. Well, you can see that by the time you get back to the zero B field that you've put on, we're now reversing the external field, that the material is still net magnetized because this field can't overcome all of these spin-spin interactions at one go, and indeed you have to go to a significant field in the opposite direction to go through it to back to zero magnetization. Then likewise, as you keep making this field larger in this direction, you now are gradually starting to flip all the spins over until finally, if you apply a large enough field in the opposite direction to the one that you've magnetized it in the first place, it saturates the other way. And this state down here of saturation corresponds to all the spins lined up in the opposite direction. And then again, if you start with this state, and now you go back and put the magnetic field again in the original direction that we used, again, it's symmetric with respect to this point. You get to, when you get back to zero applied field, you've not lost all the magnetization. You have to put on a significant field in the opposite direction to get the spins, if you like, back to random. And then finally, if you keep the field going in this direction, you come back up to this point. So this curve is a very complicated result of quantum mechanics in terms of the original idea of why these materials have got spins that line up in the first place. Then it's deep in solid state physics because you've got all these grain boundaries being reorganized. So it's a very fun, although we can write down some equations for magnetization which sort of make the Maxwell equations look a bit easier inside these materials, bear in mind equations like this are actually not really applicable to ferromagnets, and they do produce some slightly weird kind of answers. So we've got this very complex phenomenon. That's why ferromagnetism is the last of the original lectures of the course, because it is actually the most difficult to understand. So most of the rest of the lecture is just going to be on how we deal with that in a formal way, because as I said, the classical electromagnetism doesn't give us much insight into the problem really. So if we do take this, go back to this analogy and say, well, actually my magnetic dipoles are effectively like little currents going around, then the way that we would look at a magnetized iron rod is as shown in figure 129. But first, as I say, I'll just start. I've got few enough blackboards in here, so I can't afford to keep my periodic table up. We'll get rid of that. But you know, I brought that in to emphasize that, you know, we are in a world of quantum mechanics, which we can't really explain. So you've been warned now that a lot of this classical analogy that we're going to go through in the last sort of half hour of the course is a little bit dubious. So let's, however, pursue it. So now imagine that we're looking at a bar of iron, and all the, if you like, the magnetic dipoles are pointing out of the view graph at you, we could say that, so the z direction's pointing out of you, and that would be the magnetization direction. The dipole is perpendicular to these supposed circulating currents. Well, in effect, and this is very like when we went over Stokes' theorem at the beginning of the course, you can see that if it's uniformly magnetized, all of the little circulations inside will cancel out. That's only true for uniform magnetization. In fact, just like in non-uniform electric dipoles, if you have a non-uniform magnetization and you don't get cancellations, you get a very, very complex problem indeed, and you can get, if you like, effects both inside the material and at the edges. However, if it's uniformly magnetized, we've got inside this cancellation of effects. And this, as I mentioned, we actually looked at this when we were looking at Stokes' theorem itself, that when we looked at Stokes' theorem and we were getting this very important relationship for electromagnetism, we precisely said, well, if we take that little cell, the circulation is downwards, but if we take this little cell, the circulation's upwards, and it cancels out. And the only place it doesn't cancel out is around the outer loop. So for a uniformly magnetized material, and as I say, with these complex solid state phenomena going on inside, that's by no means always the case. But if it's uniformly magnetized, then basically you get a cancellation everywhere inside, but not, of course, at the outside. That loop there's nothing to cancel it on the outside, and you end up with a circulation of the field around the outside. So if we've got a rod that's with its magnetization perpendicular to this plane, it's equivalent to, I'm not saying that is really a current flowing around the outside of a bar of iron, but it is equivalent to having a circulation of current around the outside of the bar. So, and again, rather amazingly, he had a kind of extraordinary vision. Again, I think I put this up earlier in the course. This was Maxwell in 1861, and it's almost like a visualization of the conceptual problem that Maxwell said he had himself. He found it very difficult to visualize that all these, so he called them molecular vortices, could coexist with each other because there seemed to be the circulation at the same part in space, both downwards and upwards at the same time. And if you like, the behavior of a piece of iron brings us face to face with this conceptual difficulty. Nonetheless, formally, you can certainly consider a bar of iron as if it had a circulating current all around the outside. And indeed, I've emphasized right through the early part of magnetism in the course that if you have a solenoid, and that would be the current flowing around and around this long cylindrical axis, it has an identical field to the bar magnet. So we can do a phenomenological description in classical theory where we add up a lot of little circulations and we consider the bar magnet, in other words, a piece of iron, to be a simple circulation of current around the outside. But as I say, beware of that. So make some notes on the formal side of things. Sophisticated system of board rubbers in here. So ferromagnets behave in a similar, certainly not the same, a similar manner to paramagnets. They are attracted into a magnetic field, but the effect is 1,000 to 1,000,000 times stronger. And just to emphasize, before we get into the sort of description in terms of the little rotating currents, the parallel alignment of spins within a domain, and the domains are illustrated in, I think it was figure 131 of the course handout. Let me just check that with my view graphs here. So, no, sorry, the domains were illustrated in figure 133, excuse me. The parallel alignment of spins within a domain is due to the Pauli exclusion principle. It's not due, although there is a tiny weak effect that tends to line the spins up directly, in the sense they produce a magnetic field. That is a very weak effect, and the strong effect that keeps the spins locked at room temperature in iron, cobalt and nickel is purely quantum mechanical. And so we have a complex interplay of excuse me, quantum mechanics, solid state physics, because obviously we have to consider these micro domains in a polycrystalline material and the strain energy associated with the boundaries, a complex interplay of quantum mechanics, solid state physics, and of course EM, gives us the curves shown in figure 131. For magnetization, the magnetization curve is specifically the curve where we start at the origin. In other words, and as the name magnetization implies, that is specifically when we are going up curve A. So maybe put that in brackets here. The magnetization curve is curve A of, I love this lecture theatre, of figure 131, and it's called the hysteresis loop, and that's curves B and C. So this, you know, as I said, I've done the actual kind of what I would call the real physics bit first this time, just to emphasize that these mathematical manipulations that I'm going to do next are really formal. But however, you do need to know, for example, in every single textbook that you see, you will see everything written in terms of an H field, which we've not yet defined, and a B field. So it's very similar to the situation that I described with dipoles, and I only mentioned it in passing at the end of the last lecture, is that we connected this, because of the complications involved in this, we defined a phenomenological D field that was a linear combination of the E field and the polarization field. And in magnetization, we do a very, very similar effect. So I'm just going to show the maths that lead up to, poor chap, I even gave him the wrong name. Apparently he's Magneto and not Magneto Man. He's in here somewhere, lurking. So there we go. Certainly when I'm talking about the formal, the formal mathematics of magnetism, I really do feel, I've no idea what I'm doing here. But just like, and again, you'll notice the epsilon naught disappeared from that because of this strange definition of putting the epsilon naught in. And we've got the same problem here. The mu naught got defined in relating the magnetization to the B field. So this has got amps per meter and this has got Teslas. They don't even have the same units. Very awkward mathematically. But we now want, again, I'm going to leave this one out. Of course, the full Ampere-Maxwell law, as you know, is del cross B is mu naught J plus dE by dt, the full Ampere-Maxwell law. Well, because we're in a material, the E field gets modified to become the D field, so we also have to modify this term. I'm not going to bother with that. Let's just pretend that we've got an Ampere's law situation where we've got steady currents flowing around. You can see, again, this looks superficially then very similar to the so again, I'll write this out formally just to emphasize this is formal. We define an H field which satisfies del cross H is equal to. Now again, this subscript 3 here, because I've recommended the Feynman lectures, Feynman actually calls this conduction. So Magneto here is calling it J3. And we'll ignore any dynamic effects at all. Once you get in, as you can imagine, to the dynamic effects, it gets yet more complicated. So we'll just stop at the Ampere's law stage. And so what this means is that, and this is a very confusing thing, let's say we've got a solenoid. Now we choose precisely how much current we put through. And we're doing the steady state case, so let's say we're just passing a steady current around the outside of a material. Now, if we've got a vacuum inside, so with a vacuum-filled solenoid, we've got, and this is what we've used throughout. Again, I'll just write magnitudes here. We know the direction of the field. The direction of the field is just down the axis. The magnitude of that, we work that out, is mu naught Ni, where mu naught's the fundamental constant of magnetism, N is the number of turns per unit length in the solenoid, and I is the current we pass through. And now with an iron, well, let's call it iron, because this is easily the most common material that's ferromagnetic, as the name implies. With an iron-filled solenoid, B is equal to mu R mu naught Ni. Back to the crossing the room. And this is the definition of the relative permeability. And that is just the same as the definition in electrostatics of the dielectric constant, as we called it. And we know that we just multiply, wherever we see epsilon naught, if we multiply it by epsilon r, we get the modified electric field. So, I mean, there are lots of complicated things going on inside water when we put an electric field across it. There are all these tumbling dipoles which are interacting with each other. And we just say, oh yeah, but in the end, as an experimentalist, that reduces to a dielectric constant of 80. So we just like to have one number, which is a certain constant number. So similarly, where in this case, mu r is called the relative permeability. B is the real, this is what confuses a lot of people with magnetism, is the real B field including the effects of magnetisation. Now, H, in this case, the magnitude, again, it's got the same direction. Of course, if we put a current around the solenoid and we make a B field, a big B field running along this axis, of course, if inside we now insert a block of iron into here, and the domains will tend to line up like that and massively enhance the magnetic field. And I say this factor can be from 1,000 to 1,000,000. So we put on a magnetic field and we produce a magnetisation in the material. The definition is written such that H is just equal to mu naught Ni. So H is the field due to the external current, in this case the solenoid current. And there's magneto with this. Again, if we're just thinking of the Ampere's law term, well, again, because of this very unfortunate way that the mu naught got included, you would expect this to be equal to mu naught JF, but it's actually the curl of H is JF. But it's a similar equation, and so the H field is the one, if you like, that we're in control of. It seems a bit counterintuitive because in the early part of the lecture course, remember, if you've got a vacuum-filled solenoid, of course there's no difference between B and H. By definition, the relative permeability of a vacuum is equal to 1. So these two films are the same. But when you consider magnetic materials, you'd think of the H field as the one that you're in control of. That's due to the current, if you like, we pass through the solenoid, written as J free here, but it can also write as J cond, and that gives you the H field. And the B field is then a combination, a linear combination of the of the magnetisation and the current that we put on. So again, as I say, this is all very formal because in the end it's just the same problem. Because this D field's a linear combination of the external electric field and the polarisation field produced by matter, although the equation looks simple, you think, oh, I can get the D field, that still doesn't give you you still can't calculate the polarisation field inside matter because it's very complicated. Similarly here, we're in control of this H field, but then when we unpeel it and we go backwards and we want to actually know the magnetic field, we need to know this M field. And the M field is emphatically not given by a simple equation in terms of the external field. We can put in that very simple model and say, oh, the M field is proportional to the B field. But as you can see from the magnetisation and hysteresis curve, it isn't. The response is, if you take forget these numbers, they referred to a previous third year course that I did a long time ago. Let me just take those out. So this one isn't really true. This one is a kind of phenomenon. Obviously, if we combine those two equations, we get that B is this mu r times H. And so, again, in the sign, the relationship between the three fields, this is M, that's the magnetisation produced by the material. H, that's the external field that we put on. And B, which is the real field, is given by. And again, this is derived outright in terms of Stokes' theorem and so on in the VLE notes. But I thought this year, you can spend a lot of time on the formal mathematics, and in the end, you come round to the fact that this M field is so complex and not truly described by a simple linear equation that there's not a lot of point in doing a huge amount of formal mathematics. But you get that the H field, again, it's a linear combination of the two fields, and I have got the sign right. There's a lot of funny sign conventions in magnetism. And again, I make a point here. This is in Teslas, because of course this is in Teslas, but this is in amps per meter. So it's a very, very annoying situation. So again, one can derive, and again, this is done explicitly in the VLE notes, and have the usual problem in this wonderful lecture theatre with the blackboards. But if you take, you see, if you define your H field in this way, then if you then put in, and you say there's, you know, whether the mu naught comes here and comes here, you'll find about 50-50 in textbooks. I kid you not. No, people have been arguing about this for about 150 years, and occasionally there's a conference on we're going to finally get magnetic units right, and it just ends up with a fist fight, you know. And somebody sort of says, I know somebody who was taught by somebody who knew Maxwell, and I'm sure Maxwell said it should be this way round. And people say, no, that story's untrue, and nobody really knows what Maxwell said on this issue. But this is because I've referred to the Feynman lecture notes. Feynman regards it, as I do, as absurd to have the H field, which is a magnetic field, in different units to the B field. But you will see the mu naught sometimes incorporated in a different way, such that the H field is in amps per meter. But I'll stick with this definition. So if you make this definition, you can, you know, like put these two things together. If, let's say this is a big, big query, that's what this is the weak point of the whole development. If you do make that substitution into this equation, you get this very nice, simple equation here. And then clearly, if you've got this equation and this equation, you can eliminate H from this, set this equal to this, and then that gives you a relationship between this relative permeability and the so-called magnetic susceptibility of the material. But because it all depends on this highly dubious assumption, that's not a bad assumption for an ordinary paramagnet, but is an extremely bad assumption for a ferromagnetic material. So if we pursue the linear relationship, which I gave at the very beginning, but of course has now got wiped off, so I'll just put it in again, that the magnetization is given by some susceptibility over mu naught times the B field, then we can prove, and again, there's more systematic notes on this on the VLE. There's 6 pages of notes with the equations properly numbered. You can prove the mu of R is 1 over 1 minus chi B. So there is a formal way of treating magnetism. And I'd like to sort of conclude just with at least an overview of the way that the calculation runs. So that's illustrated in here somewhere. I think figure 129 I did bring with me. Here we go. Yeah. So, no, 130 is better. If you have a toroid of iron, the reason it's done as a toroid, again this follows the Feynman lectures, the reason it's done as a toroid is, and imagine that the radius of curvature of the toroid is huge, so that we can consider any local part of the toroid just to be a solenoid, and then if we do that, the H field is just mu naught n I. So you can see that this has this is in the Feynman way, where this will have units of Teslas. You can see where m gets its units from, because if you've got the m field is proportional to ni, and that is in amps, and that's in a number per unit length, so that's in meters to the -1. And so, you know, as I say, some people have this in and some don't, so it gets. But I'm going to stick, and you know, similarly, obviously, on the exam, to this system where H is in Tesla, and the magnetic susceptibility has got the mu naught in front of it. So you can see clearly, if I've divided one of these magnetic fields by mu naught, if I divide one of those magnetic fields by mu naught, I get a quantity in amps per meter. So locally, you can always calculate the H field. The advantage of doing things in this Feynman-style calculation is then all of these curves, although locally you can calculate as with a solenoid, you can, if you've got a torus, a kind of donut-shaped piece of iron, you can follow the field lines around inside, and this enables you to write, and so this is on the VLE notes, is what you do is that you, to distinguish from J cond, remember this is basically given by J cond. Of course we'd have, if we want, we'd multiply that by the cross-sectional area of the wire in this case. If you pursue this description that all these spins are an effective current, you write that J mag is equal to the curl of the M field. This is the, I say I'm only going to sketch it because I've got a couple of minutes, and so then, so this is, I've run out of blackboards, so I'll just use one of these. Sorry about that. It is difficult in here because you know, if I write, you know, like a lot of equations in here, it always ends up with, you know, just rushing around. So the way, again, this is done in detail. What I'm going through are the first sort of 4 or 5 equations on the VLE notes. This is the formal way everyone treats this. So this, note that this J mag is just an effective current. This could, you know, this is really produced by the spins in the iron. You know, it's not actually charge whizzing around in a circle. However, if we can formally relate it in this way, then, and that was 33.1 on the VLE notes, then you write, well, obviously your total J is the J that you've sent round the conductor. Yeah, that's the conduction current. That's the normal stuff, if you like. And then when you combine these ideas, this is where this kind of H field comes from. The del cross B, again, I'm just doing Ampere's law, not the Maxwell Ampere law. Well, this then becomes J cond plus J mag. And this is now equal to mu naught J cond, yeah, plus the curl of M. This is precisely popping in this definition here, which makes this formal effective current related to the curl of the magnetic field. Well, then you take this over to the other side and you get the curl of B naught of B minus mu naught M. So you've got the mu naught in front of this awkward way of doing things, is this mu naught J cond. Yeah? And then you define, this is where you make the definition, you define H is equal to this linear combination field here the mu naught m, and then you get that the curl of H is equal to mu naught J cond. And you'll see, I've done it. I always do this. I've ended up with one with the mu naughts wrong. Bugger. So at least now I get kicked in the head by both sides of the debate about where the mu naught goes in it. I've lost my mu naught along the line somewhere. I'll leave it for you to work out. So, should say, well, that's the last of what I would call the original part. I'm sorry to end up with the most messy and difficult subject, but ferromagnetism is genuinely quite a difficult subject. On Friday, we'll do the first revision lecture. I had a question about this. There's a so-called specimen paper. This course has only existed for 3 years, so there's the 2012, 2013 and 2014 papers, but when I first did the course in 2012, the Departmental Teaching Committee said this is a new course, you should give the students an idea of what the exam's going to be like, and so I produced a specimen paper. Obviously you're very welcome, of course, to practice the ones that are up there on the VLE. I'll give out copies of the specimen paper on Friday, and we'll use that to sort of focus our revision, and as I'm sure you're aware, there's quite a lot to revise in the next week or so.